sklearnutilsgraph. Description: the sklearn.utils module in scikit-learn provides various utility functions that are helpful for data preprocessing, model selection, and general data manipulation tasks. These utilities simplify common operations and enhance the workflow in machine learning projects. Inputs: data. This refers to the dataset that you want to analyze or train your machine learning models on. The data can be in various formats like NumPy arrays, pandas data frames, or lists. Parameters: these are the configuration settings for the utility functions. They control aspects like the behavior of the function, specific algorithms, or thresholds for various operations. Outputs: processed data. The output of many utilities is transformed data. For instance, data standardization, encoding categorical features, or splitting data into training and testing sets. Statistics or insights: certain utilities provide summary statistics, such as feature importance or the results of hypothesis tests, which offer insights into the data. Model selection results: some utilities help in selecting the best model from a set of candidate models by evaluating their performance on the data. Steps: data preprocessing. This involves cleaning, transforming, and preparing the data for use in machine learning models. Common preprocessing steps include handling missing values, imputing missing data using techniques like mean imputation, median imputation, or model-based imputation. Feature scaling: scaling features to a common range, e.g., 0 to 1 or -1 to 1 using techniques like standardization or normalization. Encoding categorical features: converting categorical features into numerical representations, using methods like one-hot encoding or ordinal encoding. Model selection: these utilities help in choosing the best model from a set of candidate models. Common techniques include cross-validation. This technique splits the data into multiple folds and trains the model on different combinations of folds to estimate its generalization performance. Grid search: this method systematically searches over a predefined range of hyperparameter values to find the optimal configuration for the model. Metrics: performance metrics depending on the task classification or regression. These utilities might provide metrics like accuracy, precision, recall, F1 score, AUC, or mean squared error MSE. Feature importance: for certain models, utilities can calculate feature importance, which indicates the relative contribution of each feature to the model's predictions. Visualization plots: scatter plots visualizing the relationship between features in the dataset. Histograms showing the distribution of features. Pair plots creating pairwise scatter plots of all features in the dataset. Confusion matrix representing the performance of a classification model by showing true positives, true negatives, false positives, and false negatives. Fine-tune parameters: scaling parameters for standardization and normalization. Parameters like mean and STD can be adjusted based on the data distribution. Encoding parameters: parameters for one-hot encoding, ordinal encoding, or other encoding methods might specify the number of features to be created. Model selection parameters: hyperparameters for cross-validation techniques like k-number of folds, or parameters for grid search like the range of hyperparameter values to explore. Uncertainty methods: confidence intervals estimating the range of possible values for a parameter or prediction, providing a sense of the uncertainty associated with the estimate. Bootstrap resampling: generating multiple datasets by sampling with replacement from the original data to assess the variability of model predictions. Challenges and fixes: Challenge 1: Missing data. Missing data can lead to biased models or inaccurate predictions. Sample use case: a dataset with missing values for income levels might result in inaccurate predictions for loan applications. Fixes: imputation techniques impute missing values using methods like mean imputation, median imputation, or more sophisticated techniques like KNN imputation or model-based imputation. Challenge 2: imbalanced datasets. When the classes in a classification problem have significantly different frequencies, models can be biased towards the majority class. Sample use case: a dataset for fraud detection might have a very low percentage of fraudulent transactions, leading to models that are not effective at identifying fraud. Fixes: oversampling. Replicate minority class samples to increase their representation in the dataset. Undersampling. Reduce the number of majority class samples to balance the dataset. Class weights. Assign different weights to different classes during model training to penalize misclassifications of minority class samples more heavily. Challenge 3: data leakage. When information from the testing set is inadvertently used during model training, it can lead to overly optimistic performance estimates. Sample use case: if features from the target variable are included in the training dataset, the model might learn spurious relationships and perform poorly on unseen data. Fixes: data splitting. Carefully split the data into training and testing sets before performing any data transformations or feature engineering. Feature engineering: only use features that are available at the time of prediction when building models. Challenge 4: high dimensionality. Datasets with a large number of features can lead to overfitting and computational challenges. Sample use case: a dataset with thousands of features might lead to a model that performs well on the training data but generalizes poorly to new data. Fixes: feature selection. Identify and select the most relevant features for the task, reducing the dimensionality of the dataset. Dimensionality reduction techniques. Apply techniques like principal component analysis (PCA) or TSNE to reduce the dimensionality of the dataset while preserving important information.